Actually, stochastic process is a collection of random variable indexed by a time parameter t. Okay, and then a very important ingredient when we defined stochastic process is the state space. So every stochastic process has own state space. Okay, and state space is actually, this one is a set of all possible value that xt can take, but for any t, okay, any time t. Okay, and as I said before, we can categorize the stochastic processes into 4 different types. Okay. First one, stochastic process defined on the discretized time with a discrete sample space. Second one, stochastic process defined on discretized time with continuous state space, right? And third one, stochastic process defined on continuous time with a discrete state space. And the last one, stochastic process defined on continuous time with continuous state space. Okay, and discrete time Markov chain is a representative example of the first case, stochastic process, which is defined on discretized time, and this set of state space of the stochastic process includes discretized values. Okay. And we are going to talk about such measures, some conditional probability. Okay, given that we know some information, present information and the past information, and we want to calculate the probability that the next state of the next time equals something. Okay, and then sometimes we want to calculate conditional expectation, and ultimately we want to calculate long-run averaged measure defined by a stochastic process if there exists such measure. Okay. And very important property. So before we talk about Markov property, let's define discrete time Markov chain first. As I said before, discrete time Markov chain is a stochastic process which is defined on discretized time. Okay, and state space includes discretized value or countable numbers. Okay, so for any time n, in this case, n represents time index. Okay, n represents time index. For any time n, this x sub n should take any one of the number in the state space. Okay. When you think about the definition of state space, this is very natural, right? But second is a more important concept. We call this Markov property. When you try to calculate conditional probability, so given that we know the present state and the past states, okay, we want to calculate probability that one time after, okay, state one time after equals a certain number. Okay, when we try to calculate such probability, this probability does not depend on the information before the present. And then this conditional probability is actually constant for any time n. Okay? Any time n. As long as a stochastic process is satisfied with these two conditions, then we call this a discrete time Markov chain. Okay. For a discrete time Markov chain, this transition probability is very important concept. As I said before, when we try to calculate conditional probability, so given that, let's say, current time index is n, then xn is like I, and xn minus 1 is I n minus 1 up to x0 equals I 0. Probability that one time after state after just time one time after equals j. This probability is actually the same as x given that xn equals I. Probability that x1 xn plus 1 is j. Okay, and this one is a constant. We usually use this notation, p sub ij. Okay, constant for any time n. Okay, so when we think about the transition from time 0 to time 1 and state I to j, this one is the same as state change from time 499 to 500, and state from I to j. They have the same probability, constant probability, based on the discrete time Markov chain structure. Okay. Any time n, this probability is a constant. And the second one is when we sum all the conditional probability for fixed I means state at time n. Okay, for fixed I, when we sum all the transition probability for all j, then this value might be 1, because next state, I mean xn plus 1, can take any number from state space, right? And then when you think about conditional probability, this value should be 1. Okay. Actually, the power of this discrete time Markov chain is when you try to calculate transition probability, we can use matrix form. Later, we are going to talk about transition probability from now to 10 time unit after, or 100 time unit after. Okay, we are going to talk about this later, but to calculate this, we can use matrix form, and then we can easily find the probability with the matrix form. Okay, so transition matrix is a square matrix with all possible transition one-step transition probabilities. One-step transition probabilities means this. Okay, conditional probability from xn to xn plus 1. Since we consider discrete time Markov chain, okay, they are closest random variable regarding the time, right? Just one step before and after, right? And then this conditional probability is called one-step transition probability. And as I said before, one-step transition probability might be constant in this structure. Okay. And then we can construct a square matrix with one-step transition probabilities. Okay, how many different cases can we consider when we construct a transition matrix? How many? When we construct a transition matrix, as I said before, transition matrix include all the possible one-step transition probabilities. So how many different cases when we construct this matrix? So I mean, yeah, yes. How many elements in this matrix? State space times state space. Number of state space times number of state space. Okay, size of the matrix should be number of state space times number of state space. Okay, because I can be any number in state space, J can be any number in state space. Okay, so this matrix, size of the matrix should be number of state space squared. Okay, and this low index represent what? State at time n, current time. Okay, and column index represent state at time n plus 1, one step after. Okay. Can you understand? And then next concept is how to calculate conditional probability with like over a step after. I mean, 2 steps after, 3 steps after, 4 steps after, and so on. So we are going to use some conditional probability and Markov property to derive these things. So let's think about 2 steps after conditional probability first. So if we consider this probability, x n plus 2 equals j, given that x n equals I. And we assume that we already know all possible one-step transition probabilities in this structure. Okay? Then how can we calculate such conditional probability? That's the question. Okay? Actually, we can rewrite this for all possible case in state space. This probability is the same as x n plus 2 equals j, comma, x n plus 1 equals k, given that x n equals I. We call this law of total probability. Okay? Even though we consider additional event to calculate the probability, okay? When we sum all possible values for additional events, then this probability is the same as the original probability. Okay? Law of total probability. We call this law of total probability. Okay? And then next step, actually probability, if we consider 3 different events like A, B, C, so conditional probability, okay, we can rewrite this based on the definition of conditional probability. Okay, this one is probability A, B, C over what? Probability of C. Okay. This is the definition of conditional probability. Okay. If you are not familiar with this formula, then you can recheck the slides I provided as the first class. And then, actually, this probability is the same as probability that A, comma B, comma C over probability that B, comma C times B, comma C over probability that C. Okay, and then we can rewrite this. This part might be the same as probability that probability of A given that B and C, right? Times this one, probability of B given C. Okay? So when we consider the definition of conditional probability, okay, this one actually is the same as this. For any A, B, and C, any event A, B, and C. Okay, this is true. Okay. Now we can use this part. If we consider this event as A, B, and C, okay, we can rewrite this summation for all possible case probability that xn plus 2 equals j given that xn plus 1 equals k, comma xn equals I times probability that xn plus 1 equals k given that xn equals I. We just use this formula. Okay. And then what do we know in this summation? This first term, probability, is the same as hint xn is a discrete time Markov chain. Then p, k, j, k to j, right? One step. So this value might be all possible k. Okay. This value is the same as p, k, j. This value is the same as p, I, k for all k. Okay. Right? Then we can calculate this conditional probability. Two steps after. For a given state, for a given condition, this xn equals I. And then, as I said before, as long as we figure out transition matrix, we can easily find such probability. How? Okay. Actually, this summation, okay, is the same as when we consider matrix operation. Okay, let's say this one is transition matrix P, and then another transition matrix P. Okay. This probability is the same as I slope of the former matrix P times j's column of later matrix P. Times means cross product of the vectors, right? This one, first one is Pi1, and the first one of this column P1j plus second one of this row Pi2 times second of this column P to J up to, like, if we have n states, n number of states, then P I N P N J. Okay. So as long as we have this format called transition matrix, then first we can calculate P square. Here P is matrix, matrix times matrix, P square, and then we can pick an element in the ith row and jth column. Then this value might be the same as this. Okay. How about 100 times after? First, we can find P to the 100 power, and then pick a number I in the ith row and jth column. Then the value is the same. Okay, that's the power of discrete time Markov chain. When we try to calculate, as long as we know transition matrix, and as long as we know how to calculate matrix product, okay, then we can calculate this conditional probability, like a certain time after and before. Okay.